Good morning. Let me, as usual, start reminding where we are. So we have 4 episodes so far. This is episode number 5. We had 2 lectures on thermodynamics, the first lecture, statistics, the second lecture. And there we discovered that there is something which restricts our ability to do work. And first we identified this phenomenologically. There is some quantity. So there is energy. Energy is an ability to do work, but something restricts it. We cannot use the whole energy to do work. And that was purely phenomenological understanding in thermodynamics. Then we started to think microscopically, looking inside what are actually the system that does this work. And we discovered that this quantity, which we call entropy, can be identified in the simplest way in a Boltzmann form. It's just a logarithm of a possible number of states, or a little bit more subtle, we say that this could be identified as a minus the logarithm of a probability of each state. And for n states, we assume that in this approach, the probability is 1 over n, and then Gibbs make it even more subtle. He said that generally, if these numbers are different, we need to take a mean logarithm of probability. And from now on, we just measure it in bits, which means that we take logarithm on the base 2. And that was all about work. And then from lecture 3, we started information theory. So we asked the different, seemingly different question. We said, okay, look, we have a sequence of objects, very long. Could be just a big protein. It's a set of amino acids, okay? Or it's a Bible, yeah? So this is a set of letters. And we ask the question, which is how much information it brings. And you can define this word information in many, many different ways. And we, following people 100 years ago, we decided to measure it in the amount of uncertainty that it lowers. And this, of course, follows this Boltzmann spirit to say, count how many possibilities in general there are. So one simplest way, we just look at this n symbols. Here is n capital. And we count how many different symbols are there. For example, there are 20 amino acids. Okay? So in this case, this n over here will be 20. And for alphabet will be 26, etc. So, and we just take this log and we say, look, our uncertainty is that at every place could be 1 out of n symbols. So overall, it is that many sequences possible, and this given sequence is just a choice, one of them. So the uncertainty which is lowered is this one, which is n log 2n, which means that per symbol, per amino acid, we have log of n. And then we say, wait, but we can do more sophisticated thing. We can go Gibbs way. So we look at this sequence and we counted how many times each letter appears in this given sequence. So what we obtain out of it, we obtain these probabilities, and they're generally different, and different letters. And what we discovered that this S of t is generally always less or less or equal than log n. Immediately we interpreted it, of course, there is an extra information in frequencies of these letters, and if we not only know how many letters, but also we know their frequencies, then we know more, and so every sequence brings us less information. So why do we care about it? We care because of Shannon, who have shown us that this quantity is something which bounds the average length of a word if we want to encode this sequence, for example, by zeros and ones, namely in bits. So what it tells us that there is a fundamental statement that the average code word length is larger or equal than S of P and less or equal than S of P plus 1. And then we found that the same quantity entropy now bounds not our ability to do work, but it bounds our ability, our rate of transfer information per letter. So we can decode it, and we see this Huffman code as an example how you can decode. And the general idea, of course, it's something which is more frequent, it's a Morse idea, something more frequent, you decode by short, and something less frequent by long. So on average, your code word would be shorter, and you can transfer with a faster rate. But that was not the end of the story. What was the next step? Again, looking at the sequence. Yes. We started to look at this sequence, and we started to asking ourselves what are the probability of saving J after I. So we have these 20 objects, but then how we started to, looking at the same sequence, it just need to be long enough, right? We start to asking what are the pair correlations between first neighboring letters. This is the simplest type. Now, this is a matrix, right? So before we had a vector of n numbers, now we have a matrix n by n. And of course, this matrix contains more information than a vector. What we found is called stationarity, that this vector of probabilities is an eigenvector of this matrix with an eigenvalue unity. And it's a beautiful science which I don't teach you, but you can go and learn it. It's like 5 pages in the textbook, which tells you that if you have a matrix in which all entries are positive, and the sum over all columns is unity, it's called stochastic matrix, it always has an eigenvector which has a unit eigenvalue. It's Frid-Goldman, Markov theorem, etc. And then we say that, look, we can now look at this statistics not from the viewpoint of statistics of letters, but from the viewpoint of statistics of transition from letter to letter. So we can compute the probability of every sequence as a probability of first letter times probability of a transition from the first to the second, etc. And so eventually what we decide, what we defined in this way, is a conditional probability of, I don't know, let's say J on I, but it's an average. Namely, you average over all I with Pi, and you average over all J of P Ji log P of Ji. This was the next step after Gibbs. Okay, so it was a first step. Of course, it's the most genius was here, right? And it was the second step. This is the third step. It's the same idea of P log P, because with respect to J, it's just the usual probability distribution, right? Sum over J is unity. But then we also average it over all i's. Okay? And then we say, and then again, this is generally less than this, or equal, right? Okay? And so this was a first kind of step. And then what we did, we generalized it and used it in a little bit different setting, which is now very, very universal. We say, look, if now what I obtain the sequence, for example, but it's something which has a source. So we have a source B, and it sends me signals, and what I obtain is I obtain as A. Okay? And then now we ask a different question, namely, not how much information in this A, which is this sequence, but how much information about B I obtain measuring these A's. Okay? So for example, this A's could be your genetic code. So if this is a protein, there is somewhere this A, G, T, there is a genetic code which is encoding of this. So you can look at this and you can ask what is here, the information about Z. Or another way, we ask what is the rate of a transfer of information through the channel. And this is a very general setting. This could be your physical or biological or economic system. This is your results of measurement. That could be your prediction, your theoretician, and that's the result. Okay? Or this could be your, I don't know, camera in your self-driving car, and that would be, you know, the other cars out there. And we answer to this question using the same quantity, but in a little bit more subtle setting, and it is the fourth fundamental step. It brings a new quantity. So what we say is that before we do anything, in principle, there is some statistics of B, and there is a related uncertainty about this B. When we measure A, every time there is a conditional probability that for a given A appear given B. It is this conditional probability. So I can define the same way the conditional probability of B under A. So here, this conditional probability is the information that I obtain looking at all this sequence. But now I don't have B, I have only A's. So what I say is that information that I receive is the uncertainty I had before minus uncertainty I have after. And that's the third fundamental quantity, which is called mutual information. And then we discovered that it's totally symmetric quantity. It's also S of A minus S of A under B. And this all follows from the simple chain rule, which we use in over and over, which tells you that the joint probability of A and B, you can look at it, again, we're reading it from the right, the probability of AI times conditional probability of Bj under AI. But by the same token, we can say that this is a conditional probability of AI under Bj times probability of Bj. And from this, apparently, you can also say that the entropy of S and B is an entropy of A plus entropy of BA, or it's the same as an entropy of B plus entropy of A under B. So of course your mutual information is S of A plus S of B minus S of A B, and it's a symmetric thing. Okay? So mutual information is something which characterizes a channel. Generally, it's dependent on the statistics of B and the statistics of A, and we ended last lecture by saying that then what Shannon suggested, he suggested to look into quantity, which is a maximum over all statistics of B, of I, of A, and B. Okay? And we call it capacity. Okay? It's just a definition, right? And as we ended at this point, so now today's lecture starts. So first of all, why would you introduce this? The only justification for any definition is that it's useful. It's useful quantity to look at. And it's useful quantity in a sense that it orients us to look into P of B, choosing different inputs if we're going to transfer information. For example, if you're measuring physical system, you don't control P of B. It's not under your control. But if you are sending messages, or if you are encoding your sequence, so nature need to choose how to encode this by this, and so you may answer. So just to be, let's look at the examples, because it was all general, and now it's much better to. So if I consider a simple channel, again, we're now talking about this quantity, this arrow. It's called channel. It's something which is characterized by this. So if we take something which is binary channels, it's binary. Name that if it comes 0, it transfers 0, or if it comes unity, it transfers unity. What is the capacity of such channel? 0. Capacity of such channel is 0, namely you cannot transfer information through it. Capacity is a maximal rate of information transfer per tick, right? How many bits you can transfer every time? One. One bit. So you send one bit is a choice between 0 and 1. So you make this choice. You send 0, it comes as a 0. Is it for any statistics? This is your B, and this is your A. Is this one bit for any P of B? What would be the rate of transfer of information of this channel if I transfer with the probability 1 over 4, 0, and 3 over 4, 1? Just like have such kind of a code. Remember this Huffman code, which had 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. You see, there are more ones than zeros, right? So if you're using Huffman code for this, so you see that there are more units than zeros, right? What would be the rate of transfer over here?
Less than 1.
Less than 1. Well, we can compute it's just 1/4 log 1/4. So again, the capacity is 1, means that you need to find such a statistics of B, which is 1/2, 1/2. Only for this statistics of B, where in your input you have on average equal number of zeros and 1, then your channel transfers 1 bit per symbol. Okay? Good. Now, let's go. I just want you to get used to capacity, so we'll play a few things with it. So now my B, and that's my A. So I have two possibilities of B's, but my A is a device which has 4 regions. Okay? And so again, the same question, what is my C? How many bits this channel transfers? One bit. Why? Again, this is maximum of mutual information. Right? This is a formula for mutual information. For example, if I'll try to, let's try it, is S of A, and again, it's max over P of B, S of A minus S of B, S of A under B. What is S of A? What is the entropy of A, which is 1 over 4 possible 2? So this guy is 2, and this one is? What is the entropy of B if I know A?
0. No. 1. This
is
entropy of A if you know.
This is A of B, sorry. This is A is in the first position. So if I know B, I don't know exactly A. For every B, there are two possibilities, which mean 1 bit. So indeed this is 2 minus 1. Other way, I can write it as S of B minus S of B under A. Now S of B of course is 1, and this is 0. If I know A, I definitely know B, right? Okay. So anyway, I look at it, I get 1 bit.
Doesn't it depend on the probability of whether you get 1 or 2 if B is 0? Like the distribution of these three?
Yeah, here it is independent. It's dependent how often I use this one. Okay.
But if whenever B is 0, A is 1.
You mean
always.
whether it depends on,
Yes.
I can have here 1/4 or 3/4.
Yes.
Okay, then in this case, if you look at it, your entropy of A will be different, but your conditional entropy will be different. If you look from this perspective, then again you see, if again, now you need to choose with equal probability this one, okay? But this is 0, okay? So it's still 1. So it does not depend on this, but it does depend on this. That's the genius of Shannon, okay? It's the maximum over P of B. Okay? That's what it is. Because its capacity already asymmetric. Mutual information, just I finished. Mutual information is symmetric, right? The degree of correlation A with B is the same as B with A. It's very dramatic. You remember that last time we discussed that you have impurity in your crystal and it's 10 to 23 possibilities. And you have 10 readings of your device. So exact knowledge of reading of your device tells you as much information about position of an impurities as an exact knowledge of a position of impurities, 1 of 10 to 23, tells you about device. So mutual information is symmetric. Capacity is not. Okay? Because there is a direction in which it goes. Question?
Yeah, I'm wondering about the definition for the max over B. So are we assuming that A defines the channel?
Yeah.
Or the channel is defined
The
independently of A and
channel is the relation. When we come to perception and all this stuff, the channel is how your eye sends to the brain. Okay? Now, what your eye gets is B, statistics of B. Okay? And sometimes in some environment you don't get much. In some environment your eye works very well. But that's statistics of it. Okay? So, but this is a technological this is a technology of how it works. Okay? You assume it's given. Now you ask for what inputs it would work best. You call this capacity of this technology of transfer. Okay? Good. Third case. So let's. So now we'll look at B, which has 6 position, and we'll look at A, which has 6 position. But we'll do the following correspondence. Well, you get the gist. Well, still, I finish all my errors. Okay, it's perfect. It's kind of it's on a ring. Okay, so what's the capacity? There is a formula.
And all connections are equal? Like
Yeah,
FF?
it's a good, but then again, as we already discussed, it doesn't depend on this, it depends on the statistics that you have over here. So now, but generally at this point, you can just look at your S of B and subtract S of B over A. Or you can look at S of A and subtract S of A under B.
Log of 3?
Huh?
Log of 3?
So first of all, this is log 6, both of them, right? And this is log 2 for both of them, right? So if you know this, it's just 2 possibilities. If you know this, it's just 2 possibilities, right? So it's log 3. It's like for this intersections, okay? Which means that essentially, and now you may ask what it is this P of B on which you have this rate of transmission, and it will also be error-free. We now start talking about errors. Okay? So what kind of input you need to choose here if you want this channel to be error-free?
What do you mean by error-free?
This I'm again because I'm inductive, not deductive, so I'm trying to bring you to this. Why this is so hugely important? Because it's hugely important because it sets you error-free rate. So error-free means that for every A that you receive, you get B exactly. Because generally, if you would be using this and this, and you would get this, you cannot distinguish, right?
Get only every other second one.
Yes. So your P of B, this guy, which corresponds to this C, which would mean that you just choose 1/3 0, 1/3 0, 1/3 0. For this and now exactly you can look at it and say that now it's 1-to-1, it's error-free, and of course logarithm of it is exactly equal to capacity. And that was motivation for Shannon to think about capacity and to prove the most important theorem of information theory, which we'll discuss today. And I'm not going to prove it to you but I'll try to give you understanding of what it's all about and why this quantity is so important. But on this example, you see what does it mean to choose. In these cases, it was simple. It was just maximizing entropy of S of B. Because our transmission does not depend on S of B. So you want to maximize this quantity, right? Which is this one. So this is given, right? This is how your I works or whatever. So you try to maximize this and you choose uniform distribution over here, right? But what it also shows you that if you have such case and you really not only want this rate, but you want this rate to be error-free, then you need to choose very non-uniform statistics of B. Or, as they say, non-overlapping. Okay? But this is a simple inductive example. And now...
You can't always be error-free, right?
Okay, before talking about Shannon theorem, let's just look at it as if we are trying to be a genius, okay? So, let's say now you're doing the following thing. You really have errors, I mean, not just kind of something glued together. So, you have this channel, binary channel, and with probability P, it sends 0 to 0. I don't know, yeah, let's say 1 minus Q, and this is Q. But with probability Q, it makes an error. Okay? Now, it's the same when you have 1, again, with probability Q, and this is 1 minus Q. Okay? Which means that you're working with it. Every time you send your bit, it can come flipped. Okay? And now Shannon, what was his main idea, is that look at large N. The main idea of information theory or communication theory as Shannon did it is the same idea as thermodynamic limit in physics, look at large N. And people will say, so what? So you have many, many bits, but still you can make error at every step. And then Shannon showed the following, proved the following theory. He says that if you have, in this case, you have the your uncertainty, your entropy, right, is S of Q is minus Q log Q minus 1 minus Q log 1 minus Q, right? That's an entropy of this. And what Shannon has shown and what we'll now discuss is the following statement. That if you use a rate of transfer which is less than your capacity, which in this case is expressed through this, then your probability of error can be made exponentially small with the rate c minus r. It's a very, at least 70 years ago, was very counterintuitive statement, right? It was a statement that there is nothing about how you do error corrections. This is a big, industry which is just getting bigger and bigger with every day. But it was a general statement about laws of large numbers, okay? And now I want us to discuss it, okay? But we now discuss this most general case, which means that not only you have something glued with a probability kind of in a dynamic way, but and in this case it's simple. You can just this, but again, look what happened here. You lowered your possible inputs, which means that you lowered your rate of transfer. That's what exactly Shannon tells us. Your rate of transfer need to be less or equal than capacity. Okay? So now let's look for this channel and look at a large n sequence. Okay? Well, first of all, let's plot this quantity. S of q. Okay? So in this case, S of q is this. When q is 0, it's 0. When q is 1/2, it's unity, and then it's 0. What is your capacity in this case? What is the capacity of this channel? By definition, it's S of B minus S of B under A. What is S of B here? It depends on P of B, right? Let's choose it half-half. Then we already know there will be a maximum. That what is this? 1. What is this? No.
Q and Q.
Is this S of Q. The conditional entropy of B under A, it's a statistics of your errors, right? So when you know A, you still have uncertainty about B, and this uncertainty is characterized by this probability distribution. It's maximal over here. So it's 1 minus S of Q. Now we see that if probabilities of making an error is 1/2, capacity of my channel is exactly 0. But if the probability of my error is anything but 1/2, it immediately positive, no negative. Okay? Is that clear? I want you to meditate a little bit looking at this formula. Okay? So errors, Q, means that even when I obtain A, I still have uncertainty about B. This is my conditional remaining uncertainty. That's my mutual information. Well, C is the maximum, but we're already choosing half-half, and that means that we already reached the maximum. Okay? So that's a statement of Shannon is, this channel has a capacity which is 1 minus S of Q. Okay? Now let's see how it actually works. Okay? So I have a very long sequence, n sequence of transmission through this channel. How many errors I have? Q times n. So I have n symbols and I have qn errors into it. That I know. Without obtaining any signal, I know this because I know the error probability. This is something which I built, right? So now I am asking how many ways to distribute these errors. This is precisely how Gibbs wrote this formula and how we say that if you just count probability of letters, then your uncertainty is where are these letters standing. So you need to count the number of orders. In this particular case, you need to count the number of positions of your errors. Because when you will be doing error correction, you will be exactly trying to send as much information to identify this position. So first of all, you need to count how many possible positions, or in other ways, how many possible vectors. This is a vector, right? Huge vector in n-dimensional space with these different positions of errors. So how many? By what I need to divide? Qn factorial 1 minus q. Well, let me write it. N minus Qn factorial. Okay? So this is the number of ways I can choose Qn out of n. Okay? Now, if I take log of it, and so this is 2 in the power n s of q. Okay? So this is a number of possible things that I need to identify. I need to identify where my positions of errors, which means that I now need to send m extra bits. Right? It's still non-constructive. I'm not telling you how actually you correct it. I'm just saying you that this is your uncertainty. This is how many possible positions of errors, namely there's out of which set you need to choose which one is, right? Because when you choose, you say, okay, errors are in this position, which means that the receiver flip every bit in this position and get exactly correct message. So now you say that if you have m extra bits, how many possibilities it would give you? Bit it's again that you have two positions. Okay? So at every such bit there could be either 0 or 1, and 2 to the power m is the number of possible the number of possible vectors of these positions of Q. So what now you say that this at least must exceed this. This is the number of possible positions of errors, or number of sequence with Qn errors. And this is the number of extra bit, which means that you require that your m is larger than your n times s of q. Okay? But now, if you send in extra m which do not convey the information about b, right? These extra m bits, they contain information about your errors in your channel, not about inputs over here. Which means that now your effective rate that you use is n, which you sent overall, minus m, which was totally irrelevant to the information about b. And because it's rate, then we need to divide it by n. So this means that this is your rate, and because m is larger than s of q, then your rate is less or equal than 1 minus s of q. That's which is capacity. Okay? This is just counting.
Can you repeat the problem and what are those extra bits? Who
Just.
sends them and
Okay.
why?
What I'm now saying that not telling you how you correct errors. What I'm telling you is the following thing. So you have B, which is your information, which you need to transfer. But what you know that your channel, which transfers, is something which makes error with a probability Q. It's a simple case, just binary channel, one number Q defines it all. So now what you say is that if you have in a very long sequence Qn errors, then there are that many positions of these errors. Okay? So it is that many possible positions. You need to identify this position, which means that you need to send extra bits, which is at least that many bits as their positions. Okay? Because there's bits that m is a rate, so 2 in the power m is a number of possible combinations. Okay? So now, because this must be larger than this, it tells you that m must be larger than S of q. Now, this m you need to subtract from your rate. Okay? Yes?
Do we not have to take into account that the m collection bits can also have errors? So we need to collect them.
Good question. Yeah. And generally, for example, how it works as a sample, there are some things in which your this error correction by itself would not have errors. But there are also situations in which they could have errors, which means that you also need to do this kind of iterative scheme, etc. Okay. So now this was just counting, and in particularly, if we come back to proteins, you remember that there are 20 amino acids. So you would say that the rate, when you just look at your original, it would be just log of 20, which is like 4.5 bits. But when you write it in a genetic code, where is my, yeah, this one. So, but when you look at the genetic code, you find out that there are 4 such guys. Okay? And we encode it by a triplet code. So every amino acid is encoded by something like AAG. So we have 4 in the power 3, which is 64. And that's a redundancy with respect to, so this is log of 64, it's log of 64 is 6 bits. So we see that when we use encoding by bases, we use more bits than is needed to encode amino acids. And of course, this is error correction. And now this error protection, in this case it's error protection, it was kind of error-free in the following sense. That, for example, you have AAG and AAT, right? Which means that something by error flipped over here. But you use a code in which this would be the same amino acid. So it's totally error protected. But it's error protected for the price of sending extra bits. Right? So there are kind of different ways, but the general message is that you have possibility of errors, you need to send extra bits, and it is precisely capacity which measures it. Okay? Now let's make a break. You meditate about it, and after the break, I'll not prove the theorem, I'm not mistaken, but I'll give you at least a language in which the theorem is proved. Okay? 15 minutes.
How do we define the rate? Like, what's the definition? That's the information in specific.
In this case, it's just in every position how many possibilities.
That's the definition of R?
Yeah, in bits, yeah?
Okay, so again, so why is this the formula for R? Like in this case? Like, why do we subtract and divide? Like, why is that the correct?
Look, if you would be just encoding every one, if this, your sequence, would be just bit in every position, then your rate would be 1, right? So you send 10 bits per n. Now we're saying that no, my rate is actually that not that I send.
Oh, it's how many information bits I send per bit. That's the definition. Okay. Okay.
I would like
Yeah.
you want to make some coffee?
Yeah, okay, let's let me just answer it.
Because I would like to. The guy asked you a question about the actual meaning of the extra n bits, and then you explained it with the amino acid. I would like to maybe repeat the explanation because I didn't get that one.
There are many ways to send extra bits to correct error. For example, some extra bits are sent, they compute the sum of zeros and one in some position. And you know that in your right message there would be must be always even. So there are some extra numbers which just send the sums. Okay, this is one way of sending extra bits. Another way of sending extra bits just originally using encoding, in which some things are encoded in different ways. Okay, so instead one-to-one correspondence between amino acid and genetic code, you have not one-to-one correspondence. You have several genetic combinations of bases which correspond to the same amino acid. Now you protect of randomly changing on the way in the transcription.
All right. So what we're proving here is
So
not.
there are many ways to do this M, but is this M at least must be larger than S
All right.
of Q?
I'm not telling you the method. I'm just telling you the optimal method is kept
cannot-
with M extra information added to the work.
What I'm saying, you cannot do better than this. Right? You want
Right.
your M as little as possible.
Wow.
The answer is this. You cannot make it smaller than this. That's all the statements. It's a very trivial combinatorial statement. Okay? No matter how you do your error correction, could not be better than this. Then your rate could not be larger than this. That's why your capacity is really bound your rate. Okay? And now I'll try to show how you actually.
איך שאני הבנתי את זה בסוף, זה שההגדרה שלו זה כאילו זה כמה ביטים של אינפורמציה, אני כאילו, היעילות של ביטים פר ביטים, כאילו אז אם אני...
יעילות הביטים, זאת אומרת הרייט הוא יותר נכון efficient, זאת אומרת כמה אינפורמציה אני באמת מחזיק בכל ביט שאני נותן, וזה יהיה פחות מאחד, כי אחרת הביט שלי היה מושלם.
כן, כאילו, אני חושב, למרות שבאינטואיציה שלי זה אמור, כאילו לפי ההסבר שלי זה אמור להיות n חלקי n ועוד m, אני מניח שמספרים גדולים זה נהיה שקול, אבל אתה שולח, רוצה לשלוח n ביטים של אינפורמציה, אתה שולח את ה-n של האינפורמציה פלוס n של...
דווקא זה כן קצת צריך, אתה אומר, הדבר הזה בסוף הולך להגיד לך מתוך כמה ביטים כאילו אני הולך לשלם על החוסר הטבעיות שלי.
כן.
נכון? זאת אומרת, כאילו ככל שהאם הזה יותר גדול ביחס ל-n, צריך לשלם יותר אקסטרה אינפורמציה בשביל לעשות את זה.
כן, כן, פשוט אומר, גם בנוסחה הזאת זה קורה, כאילו סתם...
אתה צודק.
לא, כן, זה סתם כאילו... לא, זה סתם זה הלוגיקה שלי של לשלוח...
אני חייב להגיד שכשאני עושה את המעברים האלה,
אז תמיד, כן. כן, כן.
go prove it that time, right?
Okay. So yeah, still there is one more minute. There is no tutorial tomorrow, guys. It's time for you to start solving problems from the book. So last tutorial I just shown more or less how to read the solutions in the book, right? So, namely, always ask yourself why I included this problem into the book. Because I include them only if there is some surprise, something interesting, right? First of all, you're grown up, so you know you try to solve the problem yourself, and the exam problems will be all from the books. Okay, so there's no tutorial, and there is also second quiz online. I hope you all finished with the first one, right? Okay, so let's finish this story. So
is the second one already open? I think it was written that it's open like in the 20-something.
yeah, there will be, I guess, next week. Yeah. Okay. So again, if I have a perfect channel, which I just erased over here, right? Which does this, then its capacity is 1, and I'm sending n signals, then I would get n bits. So my rate is n bits divided by n, my rate per bit, and it's unity, and it's exactly equal to capacity. Okay. Now the idea is the following: that and I'm trying to give you an idea of a proof what Shannon did, namely proving of this statement, error. And the idea was the following, that generally now you have a rate which is less, okay? So now you ask, what is the rate? Rate is essentially how many bits you send. So in this particular case, out of your n, there is only Rn that you use for your useful information about B, okay? So in this case, it is that many possible code words, if you wish, right? So there is that many useful bits and that many possible code words. And what mathematically, when you try to prove about it, you think about every such thing as a vector. So any sequence is a vector in some very multi-dimensional space on which your coordinates is the real bits which stand here or there. Now, when errors are made, then it's not a single possible code word, right? There will be different possibilities of different errors. So you think about it in the following way. You say, there is a sphere. So it could be here, this vector. It could end here. Because changing 1 bit, 2 bits, 3 bits, changes this vector a little bit in your multidimensional space, right? So this is the way. So you say that what is actually happened when you say that now how many are dots in this sphere? So you have a point, right? And now you can go and make Qn errors in this thing, and then you need to estimate exactly what we did. How many possible positions of these errors? Every possible position of the error corresponds to a different vector here, right? Because this vector is essentially, its coordinate is the position of your bits in the sequence. So then you say that the number of dots or in this sphere is 2 in the power n times s of q. Because that's precisely how we estimated the number of possible things. Okay? So now, I mean, what this mathematical language in which you actually prove it is the language of vectors and their diffusion because of errors. So what this theorem says, I mean, look, making errors is just diffusing every vector like this. And then there is another vector, another sequence. And it has its own sphere of errors around it, right? And so what you want to require, and again, what is used here to prove is that n is going to infinity. Namely, this is a very, very multidimensional space. It's a very, very long vectors that you have. And there is some diffusion over there, okay? So what you really want is that you now say, okay, that many code words I have, each one diffuses into this. So if I now take 2 in the power nr plus ns of q, namely the number of possible vectors times the number and how many it can branch over this at least must be less and essentially much less because s going to infinity to 2 in the power n, which is the total number of possible vectors in this space if you would be because this is the length of your sequence, right? You say that this is my rate of information, this is my diffusion of errors. So if you want them asymptotically in the limit non-overlap, and essentially the Shannon's formula is a probability of an overlap, right? So now what you find out that when you find when you divide this by this, you find out that it's 2 in the power, what is it, n, what comes here, 1, what comes here, minus s, what comes here, minus r. So this is your degree of an overlap, right? So this divided, well, with a minus, so this divided by this. But this is exactly 2 in the power n c minus r. Okay, minus. So as long as your r is less than c, asymptotically in the limit of large n, the overlap between errors made out of here and here will be exponentially small. So when it's formulated in this way, it looks trivial, but it really was something very surprising at the time, this statement, and it's non-constructive. It doesn't tell you how actually to correct for these errors. Okay? But the logic here is, at least the mental picture, is that it's a very multidimensional space. Most of the tricks in the first series is built on this thermodynamic limit and on the fact, and when you look at how, for example, LLM models work, they also do something in a very multidimensional space. And there's a very non-trivial geometry in multidimensional space, and combinatorics very different. But in this case, it's just a statement that when n goes to infinity, what you really need to make is that this number is less than this unity over here, and then taken in the power n, it would guarantee you exponentially small probability of errors. Okay? So that's why this quantity is so important. But it's unusual information, right? It's S of B minus conditional entropy of B over A, right? It's exactly what stands here is C maximum over P of B, S of B minus S of B over A. That's your entropy of an error, which is S of B over A. That's your unity, your entropy of B, when you choose maximum.
Where did the first inequality came from? The 2 to the power of p is smaller.
Yeah, I'm saying this is the number of my sequences made with errors. This is the total number. And this, when I divide this by this, would be the degree of overlap. Because if it's of order, then they're kind of close to each other, right? So you have number of vectors, and you have another number of vectors. This number, when it's small, then it will be, okay? So at this point, I'll go to the next subject, which is, again, it's the same subject, but continues to illustrate the power of this quantity, which, let me write it again, is I of A, B, S of A plus S of B minus S of A, B. So, and now I want to also illustrate it, that a power of this quantity, and particularly when we come to quantum information, the entanglement entropy, which is to a large extent similar, is that it's a difference. And as a difference, it's something which made it extremely useful and helpful in things which tortured physicists for about 100 years, and it's a continuum. So far, I pretended that we're always discrete. We were always counting, right? But again, when we start transmitting signals, we understand that there is an error, and as long as we aren't quantum people, then there is kind of a continuous possible distribution of errors or anything else. So what I now want to show you briefly how this quantity really allows us to treat continuous limit. So, for example, if you look at continuous line and you ask what is the probability, and it has a length L, so it's finite line, and so you ask what is the probability of find the point on a line? It's okay, this whole probability must be unity, so integral, etc. But then you say, well, look, it's continuous, right? You need infinite amount of information to define the rational number. And you even want to define irrational number, right? So what logarithm of what I'm going to take? You say, okay, look, of course, there is some epsilon interval, and this is my accuracy of measurement, right? So now I have L over epsilon position, and if I take log of it, that's how many bits I need to identify the position of my particles. Since my uncertainty is this amount of information that I need is this, and it goes to infinity when epsilon goes to 0, right? And then you say, okay, but now I wanna look at it and say that I'm just interested in the accuracy delta. Okay. So I'm interested in the accuracy delta, and now I'm interested in this measurement, and I am asking what would be the information about position that I obtain you measuring with this. So let me say that this is my S of B, right? So this is something which is now what I measure A with an accuracy of delta. Namely, I divide it by some intervals delta, that's my A, that's my device which measures it. Okay? So now, if I measure it up to delta, what is my remaining uncertainty about B under A?
Log of delta divided by?
Yes, this is the log of delta divided by epsilon. It also goes to infinity when epsilon goes to 0.
Can you
right?
show why is it delta by epsilon?
Look, now my interval is not L, is delta. Okay, so A means that I know in which delta interval my position is. That's how it works. Right? So this is my kind of initial physics. This is my atoms, and they are kind of very, very small. But I have a big device, and it measures delta. Okay? So now this is my remaining uncertainty after I shrunk my interval from L to delta. But when I look at mutual information between A and B, which is a logarithm of L over epsilon minus logarithm of delta over epsilon, it's a logarithm of L over delta. And it's finite. It's independent on epsilon. And all this physics and all this use of quantum field theory, where physicists are always interested in what actually happens when you consider very small degrees of freedom. So the mutual information is something which has a finite limit. And it suggests us to try to make a continuous limit in the following way of introducing what is called differential entropy. So let me say how you do it. So now, what you do, you take this interval of yours and you discretize it. Okay? So how you can discretize this? You can discretize this in the following way, that you introduce rho of x, which is now continuously distributed on this line, and you introduce pi's, the probability to sit in this interval, as rho of x times respective epsilon. Okay? So you position your x inside this interval, take rho, this continuous function, and so now you can take your Gibbs entropy, pi log pi, and taking the limit of epsilon going to 0, replace this sum by the integral, which would be like this. It would be an integral over dx, your rho of x, logarithm. What stands here is the probability, namely it's rho times epsilon, but let's write this epsilon, okay, because there was a minus here. So now what was standing here, epsilon dx is turned into this. And now this is it again, as any entropy, it goes to infinity when epsilon goes to 0. That's why quantum people always like to say, I mean, your information theory did not even exist in physics until h bar. Well, yes and no. I mean, this is like 30 years before Planck. But now you can look not in this quantity, but in this quantity. And this is called differential entropy. It's not sign definite, right? Because generally it could be, for example, if you take, in this case, rho on this interval L, and rho is a constant 1 over L, right? Then your differential entropy, and is usually called S of x like this. There will be confusion because at some point I will use it for Neumann entropy, but for now we're still long away from it. So this is defined as minus integral rho of x dx logarithm rho of x. And in this particular case, we would just log L. So, of course, it's nice monotonic function of L. Indeed, our uncertainty grows with L, but it could be negative if L is equal to unity. Less than unity, it could be positive. Also, if you consider transformation x to ax plus b, you find out that this quantity is not invariant with respect to this transformation, right? So take S of ax plus b is S of x plus log a. So it's invariant with respect to translation of your interval, but definitely not invariant with respect to shrinking or expanding your interval. So it's not, in some sense, it's not a unit. This is what I really want you to remember, because we'll be now using it over and over, considering why we consider continuous case? Because of analysis. It's so useful. It's so easy to integrate and differentiate, right? It's much easier than count. Ask mathematicians. They tell you that the people who do combinatorics probability are much smarter than people who do analysis. So it's very difficult. But this is now easy because of Newton. Yeah, he invented all this machinery, so we stopped thinking. We just do. We actually work like artificial intellect in this respect. Once one great mathematician explained to me that when Newton differentiated arctangents and wrote 1 over 1 plus x squared, he'd seen this picture, and he showed me the picture. He just seen geometry. And you, he told me, don't. Which means that you are like monkey. You just know that it's one. So, but that's the power of analysis, and that's why we want continuous. But I really want at the beginning to tell you that beware, right? It's not something which you naturally expect. From entropy, it's not sign definite, it's not invariant to, for example, just thinking of measure. Okay? So now I want to use this quantity and introduce so-called Gaussian channel, the things that we'll be using, and in particularly will be clear how important and useful it is, this general idea of mutual information and capacity. Okay? So now, what I really wanna do, I wanna do this B, A, and there will be noise here. Right? Exactly what we talked it in a simple case of one-bit channel, but now there will be just noise, and this noise adds, right? Namely that your A could be, let's say, linearly, but generally it could be any function which is just one-to-one function. But let's start from a linear channel, okay? But let's first compute the differential entropy of a Gaussian distribution. So let's take rho, in this case of Xi, that would be 1 over square root 2 pi n. N, because it's noise. Let me use this n so that it's not the length of a typical sequence. So it's n exponent minus xeta squared over 2n. Okay, that's my probability distribution. If you plug it here, you would have quadratic. Will be logarithm. When you take logarithm of this, it will give you 2 pi n, but there is 1/2 because there is a square root, yeah, and there is also e, which comes out when you take logarithm of exponent. It will give you x squared, so you integrate, it would give you. So e is it's 2.7, right? This is a general formula which tells you without minus. So this differential entropy of a Gaussian distribution. Of course, it's a logarithm of a variance. It just gives you an exact number because you care about normalization. But the main message is that your entropy is a logarithm of your uncertainty, and your uncertainty for Gaussian distribution is your variance, because this is the only quantity which completely defines Gaussian distribution. So this is okay. So now what I really want to consider this channel and ask, first of all, what is its capacity? Okay. So we have this channel, and of course its capacity depends on the statistics of B. Okay. Because such a linear channel. So let's start from a simple case. So we assume that the probability of B is also Gaussian, and I would call it square root of 2 pi s. And again, it's not an entropy, it's just a signal, because this is a signal and this n is a noise. I intentionally use this engineering notations because it's all about signal and noise, okay? And it's exponent minus b squared over 2s. Okay, so now we know what is s of b, right? It's just this thing, but with a 1/2 logarithm of s, 2 pi e. So to get capacity, what we need? We need condition, right? Capacity, let me remind you again, capacity, it's a maximum of a P of B, which I already kind of did, and it's a mutual information of A and B, and this is S of B minus S of B under condition of A. Okay? So what we really need to do over here is to write the probability of a given B if I measure a given A. What is this probability?
The noise probability.
Huh?
Minus the noise probability. The probability of the noise.
It's a probability of having noise xi, but noise xi is A minus B. Okay? So now it's very clear that what I would have here is it's a probability of noise, so it's n over here, and its exponent And what stands here is A minus B, that's my xi squared, divided by 2n, right? So now what I have? I have conditional probability of this, I have probability of that. So now,
In the definition of the capacity, we maximize over P of B, but here P of B is given. So is it the capacity or?
it's my usual way of cheating and jumping over things. So why I've chosen the Gaussian distribution of B?
Because it maximizes.
Why? What maximizes Gaussian distribution?
What maximizes?
What maximizes Gaussian distribution? Does it maximizes anything? Again, uncertainty is entropy. So it probably maximizes entropy. But we know that maximum of entropy is just uniform distribution.
Big numbers.
Big numbers is a nice word, but it's okay. We want to maximize entropy, namely, you remember that, okay, we want this large, right? But if I really want my entropy to be maximal under any other condition, this would be constant. Unfortunately, I'm working on an infinite interval. So if I would now take uniform distribution over uniform interval, it's 0, right? Because it's 1 over 8. For finite interval, it's okay. So what maximizes Gaussian distribution? Maximizes entropy, but it's apparently there is some condition imposed.
Standard deviation. Given the variance.
Given the variance, of course. So again, let me remind you how it's generally. So your entropy is minus rho log rho, whatever, some integral. And so now you want to say that you also have this quantity which is, that's your variance, right? And now you say that I want to now maximize not entropy, but this Lagrangian functional, which always is free energy in some big disguise. So now you're saying that, you remember we spent some time on Lagrange method of multipliers, right? So you want to find such rho which realizes maximum of this quantity. It means that now you aren't working in this subspace imposing condition. You're working in a wider space, but you now maximize this with respect to also this lambda. So now if you vary, but imagine that they are discrete, so you differentiate. So what you get differentiated with respect to rho, you get log rho, and from here differentiated, you would get lambda x squared, right? And you want it to be 0, up then you find that rho is exponent minus x squared. Yeah? So you get Gaussian statistics maximizing entropy under a given variance. So that's why I've chosen. I wanted to tell you this, but now because you asked question.
Yeah. Why is this expression of variance?
This is variance by definition. It's a mean value of x squared. This is variance.
I think this the squared looks like 1.
Sorry, it's 2. It's x squared, rho of x over dx. Okay, good. So this is just a conditional maximum. But for now, it's my motivation. I just, okay, whatever. I consider it a Gaussian input, and now I want to compute the capacity of this channel. And so now, first of all, I have P of B over A. I can also write P of A. How you write P of A?
It will be the sum of B and Xi, so it is the sum of two Gaussians.
Yeah, I can write it. Well, it's what is important here is that my probability of A made out of two probabilities of product, which I assume independent. That's why it's product. So I assume that the statistics of B and the statistics of noise are independent, right? That's why I can write this as a probability of B, right, times probability of Xi, and I need to integrate over all dB and all dxi, imposing a condition that A minus B minus Xi is equal to 0, right? So this, but again, this formula, which is really a consequence of an assumption of independence of statistics of input and statistics of noise in a channel. So now if you substitute, let me give you the answer. It's equal P of A over here is of course 1, 2 pi n plus s. You see this n, this n, this s, so this will be n plus s, and exponent, of course, it happened to be also Gaussian, 2n plus s. Again, the answer is somewhat trivial. I just wanted to show you how you honestly derive it, but the answer is still, you say, if I have an independent two Gaussian noises and I add them, and they are independent, then their variance sum together. When we'll do in 3 lectures from now renormalization group, then you'll see how it works when you will do renormalization group in adding numbers. But here we add two random. Okay, so now we can compute wait, what I did? Yeah, so now we have P of B of A. But what is P of A of B? Can we get it now without computations?
It's just Xi, no?
Huh?
It's just the
No,
Xi.
no, it's not. Xi is Xi. The probability of Xi is what? Huh? I want you to see the whole machinery of it, right? So, of course, I can compute mutual information and capacity just taking P of B minus P of A. But I can also do it like a S of A minus S of A of B. Okay? But what I want to stress you that you have a very powerful formula already for 2 lectures, you know it, which if you know out of these 4 things, any 3, you can immediately find the 4th one. And this is, it's a very powerful formula. The whole next lecture will be called bias framework, and it's just one particular interpretation.
The information is the sum of entropies minus the...
We're now talking about probabilities. So you have 4 probabilities. P of A, P of B, P of A under B, P of B under A.
The base.
These 4 numbers are related by formula which is the most fundamental formula in all this. Everything is derived from it. What is this formula? Base bias, you mean?
Yeah.
Yeah. Well, it is, but bias is a particular case of the formula, but the name of it is a chain rule. So bias is a particular case of chain rule. So let me remind you, that's what will be. So if you can write P of A and B joint distribution, I started today's lecture from it, right? Write P of A, P of B under A's. Or you can write it as a P of A under B, P of B. Okay? Which means that if you are interested in this quantity, you can always obtain it as a product P of, I have, well, P of B of A times P of A divided by P of B. Okay? And well, we can just multiply and add and all this. Okay? So last two formulas which I want to derive about this Gaussian channel is first of all estimate, best estimate, and then capacity. So first estimate is the following: that I know that A is equal to A. What is my best estimate for B? How I compute it now? Using all my
Best estimate is A.
best estimate for B.
So
My
it's
A
small.
is A. Now, what I say, okay, up to my best knowledge about this channel, B is equal to,
Small a.
no, no. Okay, before we do computations, any guess? There are two numbers which, everything is here is defined by two numbers, this number and this number, right? So we have S, which is a variance of a signal, and we have N, which is a variance of a noise. And we also have S over N, which has a very special engineering notation. It's called signal noise ratio. Apparently, this dimensionless number which rules the game. Okay? So now, what I want you, so first of all, this B, we expect it to be proportional to A. Yeah. Why?
What's the difference between them is only the noise.
Well, first of all, it's a linear channel, right? So A is related to B linearly, but it's also some plus some random noise. Okay? So we expect it to be linear, but it's a really non-trivial statement, which we'll now derive. I'm just now trying to build your intuition, that the linear relation between B, my best estimate, and A, my measurement, is linear because this is linear, this is Gaussian, and this is Gaussian. The moment you make it non-Gaussian, it won't be linear. Check. Okay? Anyway, so it's A times some function of S and R, right? Well, it must depend. Imagine that you have a huge noise. And you obtain, it's like huge, and your signal is very big. And you obtain this value of A, which is 1000. You know that most of it is noise, right? So you don't want to assume that B is 1000. It must be much, much less, right? Intuitively. So there is some non-trivial function. Right?
The noise is not symmetric.
Yeah. But again, I mean, if it's positive, then you assume it to be positive. It's kind of, okay. This already you broke a symmetry. Now you ask about magnitude. Okay? What's your, again, train your intuition. This thing, when signal to noise ratio is really goes to getting very large, namely my noise is very small, this must go to unity, right? That's okay. Makes sense. Now, when signal to noise ratio is very, very small, where this must go? To zero. So this function must be like this, right? Okay? Now let's compute it. Again, never ever do any computation without asking yourself, what do you expect? What expects this function? Like this, like this, like that. Okay? It saves you a lot of errors, a lot of wasted time. Okay, but the computation itself is really pretty simple. So what you do, you need to take, you compute B with the probability of B under probability of A equal to A. It is this probability, right? So if you, and you integrate over all values of B, right? So you take conditional probability of different values of B over which you integrate under given value of A, it's a whole distribution, and you compute mean value of it, right? The moment this would be negative, it would be shifted to negative. The moment that would be positive. Anyway, let me give you an answer. It's A SNR 1 plus SNR. right? So it's a linear function of n, but it's a non-linear function. When this is very large, it goes to unity. When this is very small, it goes to 0 linearly. Okay? And the last thing, it's a capacity or a mutual information between A and B, which is of course S of A. I can write it in two ways, but let me A under condition of B, which is S of A minus S of B plus Xi under condition of Xi, under condition of B, and this is S of A minus S of Xi under condition of B, and this is S of A minus S of Xi, which is not surprisingly, and this is logarithm of A has S plus N, and Xi has N, right? So my entropy is a logarithm of a variance. The variance of A is S plus N. The variance of Xi is N, is noise. Or you can say that this is n its 1/2. This is important because it's everything is in bits. So it's 1/2 log 2, 1 plus SNR. So that's the capacity of my channel. I did not prove that it's, but it's really expressed in terms of what is given. And in this sense, what is given is the ratio of a noise to the variance of a signal. And under a given noise, it corresponds to a given variance of a signal. And for a given variance of a signal, S of B is maximal for Gaussian distribution. This explains why I took Gaussian distribution, but essentially we also derive it by finding Laplacian Lagrangian mask. Okay? So that's the end. So this is a finite set. So first of all, what was today's lecture about? It's about mutual information, and capacity is just its maximum. So there are two things which are useful about mutual information, which I want you to remember from today's lecture, is that first, it's something which determines the quality of a measurement, transmission, prediction of a relation between A and B. And second, that in the continuous limit, because it's difference, it's something which is independent of your resolution. In the limit when resolution goes to 0. When your entropy goes to infinity and your conditional entropy goes to infinity, the difference between these two, which is mutual information, stays fine. Okay, that's really important. And in particularly, what we computed here, we were working with differential entropy as if it is an entropy, right? That's why what we really were working is that we were interested in the capacity, and the capacity is a mutual information, and of course you see how much sense it has. So when your signal to noise ratio goes to infinity, it's essentially a logarithm of their ratio, right? Which means that that's precisely how many values of input you can distinguish. If its variance is like this and your noise is like this, then this variance divided by this noise, it would used to be n, so it's a logarithm of n, of possible distinguishable values of an input. On the other hand, when this thing goes to 0, it goes to 0 linearly, right? Which still tells you that you can get something about it, but it's a very, very small mutual correlation, which is mutual information. Okay? Questions? Okay, good. I must admit that it's not my best section in the book. I really didn't like it. This morning when I reread it, second edition will be better, but then again, read it several, that's why you can get it. And there is no tutorial tomorrow. Solve the problem.
יש משהו על ה... 2 בעצם נסביר על פשוט בשני גרפים,
זה היה בשיעור הקודם.
כן, כן.
אז כל קבל החלטה מודעת שאני לא מגיעה לסמינה. אני איך אמר?
בחלק הזה, שאז נתקעתי את ההסבר שלו של למה או שהנוסחה הזאת, מה זה מתאר?
זה מתאר את ההסתברות שלי לטעות. כלומר, מה הסיכוי שאם אני...
שאת לא טועה ברצף.
כן, אבל לא רק שאני טועה, אלא שאני מגיעה למקום אחר לגמרי. כאילו, זה ה... ואז מה שהוא עשה, כאילו זה כל המשחקים שהגדרנו את הקיבול של הערוץ בתור אחד פחות S של Q. אז אמרנו שכמה ביטים אנחנו צריכים כדי לתקן את S של Q, אנחנו צריכים M ביטים שיגידו לי איפה הטעות. ואז כמות האינפורמציה שמועברת זה סך כל הביטים פחות כמות הביטים שהקדשתי לדבר הזה, ולכן הגודל הזה הוא...
אז זה סבבה, לא הבנתי את עצמה שלו אחר כך לזה. הוא היה לו איזה, הוא צייר גרפים כאילו של... ההסבר שלו ללמה זה הולך ככה. שהוא כאילו צייר את זה.
היה רצף, היה את הנקודות.
זהו. What was the point?
אוקיי, היה את הגרף.
זה כן, זה בסדר.
אמרנו שזה האנטרופיה.
כן.
אמרנו שזה 2 בחזקת M. סבבה, זה מה שאמרנו עכשיו. ואז הוא אומר שאם אני מסתכלת על כאילו מנקודת המוצא לנקודת היעד בתוך וקטור שיש לו איזשהו מרחב טעות מסוים, אז מרחב הטעות שלי הוא 2 בחזקת לא הגיוני, זה האנטרופיה שלי. ואז מה הסיכוי שלי לאוברלאפ? אז אני צריכה בין כאילו ששני חצים שאמורים להגיע למקומות שונים התנגשו.
אוקיי.
כאילו אני אמורה להגיע ל-A והגעתי ל-B. כמו ש-A ו-B זה לא דוגמה טובה. אז צריך לדרוש ש2 בחזקת N הוא R ועוד N plus Q יהיה קטן מ2 בחזקת N. כי זה סך כל האותות שאני שולחת. כאילו... אני צריכה שקצב העברת המידע ועוד האנטרופיה יהיה יותר קטן מסך כל הצירופים האפשריים. ואז הגענו, ואז חילקנו את זה.
ברגע שאני מאמין לך שמה אני מאמין לזה אז סבבה.
כן, אז זה נראה לי השורה שחסרה לך, אבל למה, כאילו הוא הגדיר את זה בתור הסיכוי לאוברלאפ, אני חושבת שאולי חסר שם עוד מילים.
בסדר, אני אסתכל אולי זה בספר שלו.
כן, אנחנו בדרך כלל עושות קריאה מודרכת, גלי ואני בימי שלישי.
בסדר.
כן.
טוב.
היום זה היה קצת יותר מברך.
זה כן, אבל בסדר.
כן. זה לא ממש לסמינר שהתחיל באחת.
אין צורך, זה הדבר יותר מנומס, זה
לא הולך למשרד. לשנות זה בכלל יהיה.
ממש אירופאי.